Thank you, Simona. Thank you for me, and thank you for everyone coming to my talk. Today I will try to confirm Hochschild and Hopf, and I will give some useful structure on both cohomologies, which gives actually a greater structure. So this is the skeleton of my talk. I will give some further construction of Hochschild cohomology, and then some basic definitions of homological algebra. And then I will introduce Hochschild cohomology, and then Hopf algebra. And lastly, I will give Hopf algebra cohomology, and at the end, I will try to construct graphical structure on Hopf algebra cohomology. All right. So, can I minimize more? Or? Okay, the algebra when A is a field and also a vector space of the field. Okay, then we define an application map. A cross A is a field, and that application map we want that to be defined here, and that's called algebra. If that application map is commutative, then we call that algebra commutative algebra. So if you think about polynomial with the coefficient in K, then the commutative algebra. Or we can think the 2 by 2 matrices with entries in K, then it's going to be what's the algebra? So we define another operation from A cross A to A, which is called bracket. And that bracket should satisfy these three conditions. The first condition and second condition is fine. First condition is kind of bilinearity. With the second condition, we want any x. The bracket of xx to be 0, and the last condition is the Jacobi identity. So if any bracket satisfies these three conditions, then we call a Lie algebra with the bracket. So if we think about any vector space and if we define bracket of 0, then it is automatically a Lie algebra. Or we can think special linear group with entries in K to what to reach with entries in K and create 0. Then we can define bracket as xy minus yx, and that's gonna be again a Lie bracket. So that will be as to SM to K, a Lie algebra structure. Okay, here's something from calculus class. So we know Leibniz rule, which is if we take the derivative of this function, then first one. What we want to do, we want to generalize this idea to first any algebra, because in here we are taking our algebra with all differentiable functions on R, but we want to make it on any algebra. That is the first idea, and then we will try to make it multi-linear. Okay, let's define derivation. So let's say there's again an algebra over K, then a derivation is a K-linear function from A to A, and it should satisfy pretty similar conditions. So delta AD should be delta A times T plus A times delta. And we notate the set of derivations by delta. So here is an example. We can think the the polynomial algebra, and we define delta xn as n times x to the n minus 1. So you use this. And so delta t is going to be equal to x, for example. Then delta satisfies the condition for derivation. So delta is a derivation. But from this example, I want to point out that this is, I mean, there A is not closed under composition because it is thing to compose this derivation by itself. So if you compose delta and delta in this example, then this is kind of second derivative, right? And we do know, I mean, we do have leading rule for second derivative, but it doesn't work like this. B is not delta A. B so this doesn't work. So that's why it's not closed on the composition. But we can define a bracket as in this case, and then it's gonna give a Algebra structure to derivation. So derivation A is gonna be the Algebra with the bracket. So delta composite, delta prime minus delta prime composite. And you can see, I mean, the first and second condition on the bracket is very clear. So delta prime is equal to minus delta plus delta, and also delta in bracket. For the copy identity, it requires a little bit computation, but yeah, it satisfies the Libra structure. So then natural question, I mean, actually, yeah.
So this example,
yeah, and yeah, for this specific example, we do have, and for any other photo, without, yeah. I should be supposed to be, yeah, I should be that is called also without them. So, and yeah, it is really painful. Okay. So now our idea. So now we are able to find the lead structure from the derivation, and we want to make it modern. So now let's define an Hochschild and cycle. It is like the definition is close to the derivation. So we take any delta from A to the n, okay, and then it is directed for Hochschild and cycle, and as you see, like that should satisfy the derivation condition as well. And if you take n1, you'll see the usual derivation there. In other words, without algebra. So we do know with algebra is a algebra, but how about like if n is greater than or equal to 2? Then unfortunately the answer to the NA is if the NA is a algebra or not, then the NA is not a algebra in general. But we want to still construct some algebra structure. But we need at that time actually we get another take the role, and then he takes all the direct sum of all the when n is greater than 0, and then he defines bracket by taking an element in empty and derivation in empty, and then he sends it to m plus n minus 1. I will give the explicit definition later, but this is the idea. And once he defines this bracket, he is able to get a graded leaf structure on the this part. Actually, I can just for now, I may write like a couple of like small degree examples here. So if we take delta in V1, A, and delta prime V2A, then delta prime is defined like this. Then the bracket should be in degree 2, right? 2 plus 1 minus 1, so it's going to be in degree 2. So it should be on 2 elements. And that is going to be, okay, delta prime minus delta prime delta 2 and plus delta prime. So it is defined for degree 1. And we have no question. And with this structure, this part is the algebra, a graded algebra. So now we can define partial cohomology. So let's say we have delta prime from a to the n minus 1 to a, and it is n minus 1 linear function. And then we define delta as in this formula. But I hope you see. So with that formula, if any delta prime satisfies that formula, then we call, I'm sorry, if any delta satisfies that formula, then we call delta Hochschild and Hopf. And the set of all Hochschild and Hopf boundaries is denoted by DNA. Now we take the quotient of it. We take Hochschild cohomology. I mean, this is how we define Hochschild cohomology. We take the n and we take quotient by n. So Hochschild n cycles over Hochschild n boundaries, and it's going to be the Hochschild cohomology n. And we define general Hochschild cohomology by taking the example. Okay, here is a small example. If we take K as any field, and if we take algebra as Kx, then the Hochschild cohomology will be 0 in all degrees when n is greater than, if n is greater than or equal to but in degree 0 and degree 1, what do we get? In degree 0, we actually get central of the algebra, which is itself, which is Kx, because Dn is, I mean, D1 is, I'm sorry, D0. D0 is just the algebra itself, and D0 is just 0, so that's why we have Kx, so this is degree 0. And for degree 1, for the D1, we have derivation. And for B1, we have 0. And so we have derivation from Kx. And also, I don't know Kx direct. So this is an Hochschild cohomology of Kx. And in general, Hochschild cohomology gives some useful information from the algebra. Especially in models, we know the meanings of Hochschild cohomology. So, for example, in degree 0, we know that we have the center of the algebra. For degree 1, we always get derivation over inner derivation, which is called arbitrary derivation. And in degree 2, we get, if I can write it correctly, in degree 2. So the cohomology, the Hochschild cohomology in low degrees gives really important information about the model. Okay, now I mean this is how Hochschild cohomology is constructed by Hochschild himself and give structure to now I will give some definitions on homological algebra, and I will define Hochschild cohomology with the way that. So let's say R is a ring and is an R module. Then we take a projected resolution of M, and it is exact sequence. So exact sequence is like kernel of the map should be in the map. And we call the bullet here a chain concept of R when n minus 1 dn equals 0. So in this case, this is another way to say kernel dn, including image dn minus 1. So basically, if you take any projected resolution in the minus chain concept. So in here, kernel dn is called n cycles, and image dn plus 1 is called n bar. And we define usual homology by taking the quotient from kernel of each. This is how we define homology. And now let's say we take the same resolution and then we apply Hopf to that resolution. Actually, apply directly. It's like a home Hopf B, and we need another model. Yes. Then we get this resolution. So resolution for around. So we get this resolution, and we omit the first part, the first term. Then we define this part here as this Dn star as is as here, and it is called cochain complex. And we define cohomology on cochain complex by taking again the term of each. And this is also how we define x1. Okay. Now we want to define Hochschild cohomology. Let's say we have field and A is a key algebra, then we have unit map from A to A, and it is given by C goes to C times 1. And the opposite algebra given by opposite multiplication. So if you do A opposite C, it is just A. Then we define envelope algebra by taking tensor product of A and A opposite. And the multiplication is given by usual multiplication, except we have the opposite multiplication for second term. So basically, this one is the then we can construct a chain complex by taking tensor powers of K, tensor powers of K, and here ends the multiplication. Then we define each differential here by this. And this is called bar complex. And now, finally, we define partial cohomology by taking again from A to the E, by applying home A to the EM to the bar complex, and we get this complex. And that complex, in that complex, if you calculate cohomology, it gives you the partial cohomology. And it is taken about for and we generally do not take n different than A. In most cases, we are interested when n is A, and it makes calculations a little different. Yeah, yeah. Oh, it can be that. It can be bimodal also, but yeah. I mean, but if you say a E module, I believe the same as the one. Oh yeah, but we generally, I mean, at a vector space, A module. So I believe both notations are fine. So if you say A to the E module, you just say A maybe. Yeah, it is, yeah, for sure it is fine. Yeah, A E module is for sure fine. So let me correct that one. Yeah. Okay, this is how we define Hochschild cohomology with the terms in homology algebra. So I will give a different example here, which is a little bit different from the previous one. So now the algebra is Kx over x2. And now I will calculate Hochschild cohomology, but I will not take line resolution. We generally do not take line resolution. We just take any other resolution because bar resolution goes different. We take n times. But we can calculate Hochschild cohomology with any other resolution. So we take each resolution here. Each term in the resolution is a model of algebra. And we arrange math as u in positive with x tensor 1 minus 1 tensor x, and v in negative as x squared tensor 1 plus x tensor x plus 1 tensor x. And we do the same thing. We just apply home again, but in here we have a useful isomorphism. So if we apply home, since each term in the resolution is the algebra, if we apply this home to that resolution, we can get copy for A. So the new resolution is something like this. And how we find the maps? Actually, I can just show one of them. So, for example, V star. This is how we define V star, right? So this is F VA, and this is kind of F 3x squared, and this is 3x squared. Okay, and then you see that V is just multiplication by 3x squared. F by V. And U, similarly, U is just multiplication by 0. So U is just 0. And we take the field with characteristic 0. So it is not divisible by 3. So I don't have problem coefficient. And now, if I want to calculate Hochschild cohomology, I just take kernel over each map. Kernel of each map over image of the previous map. So, for example, for 0, for this 0 map, what is the image of this 0 map? It is just 0. But in the kernel of this map, it is just x squared. It is just the kernel is just x. The idealism is for x. So, for any objective Hochschild cohomology, I have the idealism by x over. and you use the for even. So this is how we calculate Hochschild cohomology, but unfortunately, it's not in Hochschild. Let's see. At least we know what is the meaning, right? But do you want to learn more, like in higher? What is the class analysis? Okay, so we have yeah. I mean, for non-linear rings, they are generally defined. They are defined. So, but yeah, for any other rings, I am not sure. All right. So now we construct a Hochschild cohomology again, and I want to give you exact structure of two operations. First one is from previous slide, but the other one is cup product. So the cup product takes an element in the M, an element in the N, and then to element in the M. And it is defined as this way. And this makes Hochschild cohomology and associative algebra. And we also define the bracket structure as in this way. It is again it is like very similar to like derivation bracket. Derivation bracket in previous slide, but here it is more complicated since we are defining the bracket form variable. And again, just now the bracket takes an element in the DM, element in the DM, and sends it to element in the M plus and minus 1. Okay, so that just now the bracket satisfies again the whole comment of that, but it satisfies anticonductivity and graded Jacobi identity. So that makes Hochschild cohomology graded the algebra. All right. So let's see what is the Hopf algebra, which I'm more interested in. So a Hopf algebra has co-algebra structure. So what I mean with that is it has co-multiplication and co-inverse and antipode, and those satisfy these three properties. And it is also commutative if you have a map of a map power, so if 8 and 8, so 8 and 8, if you have power delta, co-multiplication, take that co-multiplication. So group algebra are third fine example of algebra. So if you take a group algebra and if you define co-multiplication with this way, and co-unit and antipode in this way, then it makes the group algebra Hopf algebra. But it is not too interesting because it is both complex and co-complex. So everything works fine on group algebra. So task algebra is a little bit more interesting. So task algebra is an algebra generated by G and X, and G to the N is 1, X to the N is 0, these are the relations, and XG commits it. I mean, there's commutativity, but inside the commutativity, XG equals WGX, and W omega in here is really to the and these algebra is called task algebra. And if we define for multiplication and for the and for the listed, then it makes task algebra for algebra. And as you see, it is not competitive and not competitive. Okay, I will define for algebra cohomology, but before I want to give you a demonstration which what so here are two main questions in algebra. So let's say A is a finite dimension for algebra, and we wanna find the solution, find the answer for question 1 and question 2. For question 1, we say for all finite dimensional A modules M and N, is M tensor N projective if and only if M tensor M. And we have another question, we say for all finite dimensional A modules M and positive integer 10, if M projective if and only if M tensor N tensor power M. So this is there are some fundamental questions of it. And once we define for algebra cohomology, then we can find two different questions which seems non-related to that fundamental question. But actually there are some questions. So let me mention about these two conditions. I will define for algebra cohomology later in the next slide. So let's say in here, let's say we know how for algebra cohomology. I put two conditions here. First one is for algebra cohomology finite generated algebra. The second one is the XK, X MN is finitely generated as a module over all algebra. For all finite dimensional fields. So two questions arise. The first one is does Hochschild cohomology satisfy first condition and second condition for any A, or for which A satisfies first and second condition. And the second one is more related to support variety. So if you have support variety of M tensor N, is it equal to support variety of M intersecting support variety of N for all finite dimensional images of M and N? So one of the actually Sarah Witherspoon, Chris Nagle, and a couple of more professors in homological algebra, they investigated some of the cases. For example, if your answer for question 3 and question 4 is yes, then the answer for question 1 and question 2 is yes. So there are some good relations between those questions. But I mean, this was one of the main motivations for me to start talking about cohomology. So with it. Yeah. Yeah. So is that it? So for both units. Oh yeah, I mean there are some examples. My point is that if a whole algebra that is A satisfies these two, then it was minus yeah. So but there are yeah, for sure. I mean, there are lots of cases that our answer is no for question 3 and question 4. For question 3, we have I will check again, but I am. I'm not. Okay, I will check. Somehow I remember. Oh yeah. So how we define Hochschild cohomology? We define Hochschild cohomology as K. So basically, I will show the okay, I don't want to write again, but we take this resolution and then we try to find cohomology on it, and it gives us the whole project. And I mean, we said that Hochschild cohomology has a real geometry. And we are wondering if Hochschild cohomology also has the algebra structure. So that was conjectured by Gerstenhaber and Hopf in 1992. If Hochschild cohomology has, I mean, this structure is kind of same as can be seen as graded the algebra structure. So and Heidegger and Fernandi and Karadağ, they answered the question at the same time with physical particles in 2002, and the answer is yes. The Hochschild cohomology has graded the algebra structure. And in some cases, actually, they show that structure should be namely, like if you have any triangular algebra, then the Hochschild formula, the graph of Hochschild formula. But they also show that the Hochschild formula has graded structure. But there was no explicit formula that was given in the slide. We have Gerstenhaber formula for the Hochschild cohomology. I mean, it is not useful for computation of biology, but here we have an improved formula for Gerstenhaber bracket, and we will try to construct similar kind of formula. So we take this resolution, and then we define. By the way, I want you to be like that. We can define this resolution because the algebra is all algebra, so we have only. So we can start. So we define differential as in this case, and then the lemma says the absolute resolution, which is this resolution simplified into enveloping algebra, it is equivalent to the bar resolution. And why is it useful? So our main idea, we want to take the definition of bracket on Hochschild cohomology on bar resolution, and we want to go through some isomorphisms and embeddings, and we want to have the corresponding bracket. Oh yeah. And here's a famous lemma in homological algebra, given by Shapiro. let's say A be a ring and B is a subring of A, such that A is projected as a right B module. And let's take M as a module and N as a B module. Then there are isomorphisms between that. And okay, next result given by Genzo and in 1993 that if A is a Hopf algebra and Hopf algebra is bijective one, then Hochschild cohomology of A is isomorphic to the formula. So in here, I want to mention a little bit about the bijective one condition. Bijective one, but a Hopf algebra, the definition that Hopf algebra has about this one is not really because both I mentioned the Hopf algebra, and I think they almost all know the definition of Hopf algebra. So it seems there's a condition, that is a special condition in theorem, but actually that condition is not true. And the proof of this theorem includes our differential lemma. So I want to give it, actually I don't have time, so I will not go through, but I can. So in Ekman-Shapiro lemma, if we take in Ekman-Shapiro lemma, if we take, okay, then let me see what we take here. So if we take A, B, E, A, M, A, and M, K, in Ekman-Shapiro lemma, then it gives the result. We need to use one more isomorphism, but I mean this again. Yeah. I mean we use that also, and we use also each isomorphism. We also use this isomorphism, and then with both of them, we just have the like and that had a good corollary, which is Hochschild cohomology of A can be seen with isomorphic to Hopf algebra cohomology of A direct from the cohomology. And in here, I is just talking about formula. So that is one of many corollaries from this material. So that way you can start. We can embed Hopf algebra cohomology. And by using that embedding and isomorphism, I will not go to the details because I mean the full formula was a little bit ugly, but what we do, we just we take with the lemma and X is isomorphic to AE T. So and this is exactly actually not isomorphic. This is defined is equivalent to further evolution. So we have a Gerstenhaber bracket formula on biodistribution, and we start with this formula, and we take the embedding from embedding and isomorphism from the theorem, and then we try to construct a new bracket formula for Hopf algebra, which is given in this way, and actually that's the product there on resolution T, and it is a little complicated, so I don't want to make the slide massive. So I didn't put that one, but yeah, this is the political formula for the graph structure. And I have lost a few minutes, so I wanna say, naturally, the first question is the formula. Like if it is useful or not. For now, for calculation phase, it is not. But remember, the main definition of Gerstenhaber graph and cohomology is not open for calculation. You do not do that for calculation. So I hope to get some more theory and maybe compare alternative graph from this definition. And for my next talk, next week, so here is what I will do. I will calculate explicitly the bracket structure on top algebra from the top algebra. Why did I do top algebra? Because I said that it is known that the bracket structure on top algebra from is zero if top algebra is 1. And top algebra we have non-top. So that's why I teach a top algebra and then try to find the resolution, try to find the bracket structure by finding first Hochschild cohomology of top algebra, then cohomology cohomology of top algebra, then I find them. And I will find the bracket structure on Hochschild cohomology, and I will find corresponding bracket structure of top algebra. And it turns out to be zero for the top algebra case. But yeah, that's if you don't find what you're going to then doesn't need to like generally doesn't but there is another by so if on the possibility actually we quite have to find the bracket but not about to find the bracket and some of it to give some freedom. So that yeah, that can be the calculation to but for now, I mean even these are done by some means. So even for finding I hope we will come up with can there's a lot of reference probably well, actually, yeah, for cohomology, yeah, but yeah, it is under. Yeah. So people are more interested in like content. So yeah, it makes the graph and the problem. going. But yeah, it is not. Yeah. While I was in the operation, I didn't come up with that. Yeah, that should be good.
So let's thank the speaker again.